Welcome to the new topic that we are going to discuss now in this online computer vision classes. And it's about image transforms. This is what we are going to start discuss from today. So maybe we will take one more class perhaps on this. So let me also first acknowledge that I have taken most of these slides from this computer vision course by Carnegie Mellon University, Chris Kitani, professor, I guess. And then the second one has taken slides from him and adapted it. And now I again took some of them. Most of them are either of from either of these two sources with slight modifications. Okay, right. So as I mentioned, this topic is about transforming an image. So in the first place, why do you think we need to compute or we end up requiring the computation of image transforms? Any thoughts about that based on whatever background you have got so far? Yeah, maybe I think I would give some clarity on what we mean by transforms. Okay, see this. There are two kinds of classes of transforms that you could think of. The first one being whatever is there on the left hand side, and the second one being whatever you see on the right hand side. So here he is calling it as filtering. From those who have done this medical imaging course, maybe very few, we refer it to simply as intensity transforms. So the transform is applied on the intensity of the pixels. That means, say for example, I could think of something like this. My new image, let me call the original image. By the way, before that, let me clarify something about the notation. We see an image as a function of the spatial coordinates, or the spatial coordinates could be the index values both on x and y, to be more precise. In fact, this is good enough for most of the applications, except when you are doing it in 3D with different spacing and where you need to move from pixel domain to the spatial domain. Usually pixel index values on x and y axis is what you have. So in that manner, a 2D image, you could think of it as function of x comma y, where x indicates the pixel index along the row. Okay, that could vary. Okay, in one direction this is x, and in another direction this is y. So you are varying it and you see it as a function of xy. And another compact, convenient representation is this x comma y. Let's say you represent it as a vector, simply x bar. So then you could write it, your image, as a function of x bar. Okay, in case of a 2D image, this could be simply a two-dimensional vector x comma y. If it is a 3D image, you have x comma y comma z. If it is a video, you could have x comma y comma t. T is giving you the frame number. Hope you are okay with the notations here that we are going to use. Right, this is what we use. With that notations, let me now come back here. See, the original image, let me call it as some function of x bar here. Okay, let's say I'm transforming that image and getting here g of x bar. Okay, notice here the transform here is happening in terms of the intensity values at that pixel. Okay, a simple thing I could write, for example, is g of x bar is equal to, assume that I'm using 8-bit integers, 8-bit unsigned char to represent those values. So you could think of, let's say, let me take a simple expression like 250 minus f of x bar. Okay, this is something that gives you, like when in movies, when you are going to reveal something that has happened in the past Okay, that colors would be changing. So it is not a very accurate representation of that, but it would give you a similar effect of this. Okay, anyway, here it is color image is there, so ignore even grayscale image. This works good enough. Okay, so suppose if I am doing something like this, and assume that for some reason I want to extract the key points in this image, and I do this transformation, and I apply, let's say, Harris scale invariant, or even normal simple Harris detector. Do you think there will be a change in the key points when I apply this transform? Will it be the same, or will it can it give different key points, or will it still give some same key points? What do you think?
Same key points, sir.
That's right. It has, because gradients would still remain the same. So it's a kind of same key points. Now, uh, this is one kind of transformation, by the way. This you would not key points wise detection. And what about the description now? Let me now talk about description. I have a key point in this image. Let's say it is tip of his nose. Let's say, okay, I have a key point here, and I took a key point here. Okay, on this, do you think the descriptor would change for both, or very likely it would be same?
Maybe a change in sign, sir.
Yeah, okay, that's not a problem. Sign wise descriptor gradients, it's not a problem there. Okay, yeah, you have a point. Very good. I haven't thought about it, but that's a very minimal impact which you could take into account. Okay, so your point is, since I'm taking with the negative thing, so the direction of the edge could change. That's your point, right?
Yes, sir.
Very good. So anyway, there is a minimal, okay, that's a probably that kind of transformation I applied. If I have to plot it, how would that be? This would be something like this, correct? If it is 0 to 55, this is my original intensities, input intensities here, and my output intensities are opposite thing. So yeah, well, other than that, there is no basic, there is no significant change that's going on. So that's why this is not of very high importance for us here. The scenario we encounter in most of the cases is, of course, not even this kind of images. This is another complicated situation we are stating here. So what we encounter particularly in this computer vision course is what you see here on the right hand side here. What is, so let me, before coming to the second case, let me write something here. So how do you express g of x in terms of f of x? G of x bar, I am, and just for the notation saying it easily, I'm calling it as x, but from now on you take it as a vector whenever I'm taking it. So g of x bar, okay, I could write it as, I take the intensity which is there at f of x bar, and I am going to apply some transformation on this, right? So what you could see here is, if you consider your the range of image function is what it is changing, the range of intensities that are changing here, the domain of your pixel intensities. Let's say you have an image of 256 by 256, index is changing from 0 to 255, it would still remain same here, right? Now come back here. What is happening? For example, you might be rotating your image. This is what would you encounter particularly. Let me take one example. Suppose you have taken a picture of some monument. You are now, or even a simple person, your friend, you are taking a picture. You changed your viewpoint and took another picture of him, or you have changed it, zoom in and zoom out, you changed, and for some reasons you kept your yeah, camera also tilted. Now your shift should tell that these two are same. When you take this image, okay, when you take this image, okay, then you should also, for example, want to do something on top of it. So in that case you need to align them. Okay, these applications where this could be useful, I'll come shortly in more detail. Okay, but that's something I could quickly point out to you. In that case, how do you express g of x bar and f of x bar? How do you express that? Let's say I want here g of x bar is equivalent to f of, what should I take? What should, can you say something? Just like here also you use another function transformation that you are applying there as h. Okay, so then how could you mention that? So I could write it here as f of, you are applying some transformation on f of, so what should be that? F of x bar, right? So sorry, so that's h of x. Okay, yeah, f not there was, that was a mistake. There is, I already wrote here, so let me write it better. See here, g of x equal to, from this image, the location or indices is what you are transforming and taking it. Assume that there is a translation. So earlier assume that you are taking from a location x naught. Okay, simple case of translation you call it. Now you just move your camera in the x direction. So here whatever is there at x location might be coming from in the, within the f, it might be corresponding to x plus 10 or x minus 10, right? So f of, you are applying a transform on the index. So in other words, the set of intensities that you are getting there would remain same, but the indices are changing. And of course, sometimes you have to do some interpolation if you are doing a scaling and other things. But I would like you to first be clear with the, in terms of mathematical operations here, what you are doing while you are doing an intensity transform versus when you are doing an image, like something referred to as warping. This is referred to as warping. So you are either stretching it, you are scaling it, okay, or you are applying a shear, or you are simply translating, or you are rotating. All these things you could call under the name of, you are warping the image. So here, for computing its value at a location x, you take that which is there at x only, index x only in the original image, but you would be applying a transformation on those intensities. It has nothing to do with the indices of your spatial or pixel locations. On the other hand, here you are not going to manipulate the intensities, but you are manipulating the indices here. So h of x, for example, you want to compute the value at x location, so you apply a transformation or modification to this x. For example, h of x, a simple case could be the transformation that you are applying on x could be x plus 10 in this case, right? So that's how you then shift the image, okay, or backward or forward depending on your directions of your x and y, and you are getting it. So in terms of the range of values, this changes, the first case changes you the range, here changes you the domain and range. I'm sure you are clear from the math, basic mathematics that you have studied. So is this clear before we see on which context what is required and what we will be discussing, that we will come a little very soon. So is this point clear and about this representing it, these operations mathematically? Any questions? So now let us come back to what we studied so far and see what is it that we have to do on top of it for while we are working in some of the applications. I give you this image for example. Now you all know Swift descriptor, Swift detector, or descriptor you might, detector you might use scale invariant Harris, and you could acquire some key points there. Suppose now you have taken one more image of that. So from a different direction or a orientation or different scaling, whatever it is. So you got this, these key points. Okay, some 4 key points you have got out of that. Then you want to see match these two things. Why do you want to match? Comes depending on the applications, it would you would require doing that. Okay, for example, you want to do object recognition. So then what will you do? You first find out a matching of these points. Then whether to see that object is same or not, you need to take care of bring one into the same alignment into the other object. So because otherwise if you just simply look at the scales, it would be different. So to say whether both are same or not, you should apply a transform on this image, and note that that transform would be similar to what you are applying on the right hand side here, referred to as warping. And then you bring that into the same kind of spatial size, or that's a very loose word, but the same domain you need to bring it. And then you could you do lot more other things. Some of them we would study in this course itself. So this is where you should be able to find out a transform which brings this into the size of this or the other way around. Okay, and after that you could compute some other metrics, you could do some other algorithm, you could apply on top of it and do something there. And this is even for recognition, whether this guy is same or as that guy. If you want to say, then first you should bring in one frame, he is in one image he is zoomed in, and in another it is zoomed out version of the original one, let's say. So then first you need to bring them into same scale word I'm using a bit loosely here, but that's how's the purpose. So then only you would be able to say whether both are same or different. For example, you might have extracted, I'll give you a trivial example. You might have extracted from my face some 100 key points, right? So in another image is a zoomed version of my image with some orientation change, and again you extracted there as some 100 more key points. Now whether to say these guy is same or not, what you should do is you should first bring them into the same scale using some key points there, and use then another set of key points also, not the original one, and see if that mapping, if those key points are also matching to a large extent. Okay, some because of view changes some key points could be there in one which are not there in other, but overall majority of them if they are matching, then you could say that these two are the images of the same person. Okay, this is a very loosely told stuff because we have not discussed any exactly the algorithm for object recognition, which you could perhaps do as we move on. That's one application. Then 3D reconstruction, what it means, well, this we would have a chance to discuss about it while we talk about shape from stereo, where you have one image taken and you move your camera a bit. Even that's how we do 3D reconstruction within our mind and interpret things. This is one camera here, another camera here, you are seeing an object. Now when I see the object, this is will be a shifted version of it. When I have a shifted or from a slightly different viewpoint I'm looking at the object, so that there is a transformation there. And now each pixel how much that has particular object has moved would tell us how much depth it is there at that given point. By same point, let's say here, one point here, depending on the object height variations, that's how the pixel movement in the other camera for the same corresponding object that has been seen here, that how much shift is there, that will tell me about the height. There also this alignment would be required. That's 3D reconstruction. Okay, very at a very high level, that's what it is there. Similarly, augmented reality, image stitching is something which you could clearly easily comprehend. I have taken images, okay, of like panoramic view like stuff, but individual images I want to map them. Now what I should do, I should not only find out the common key points here, but I should also find a transform that I kept them in the right alignment. Some image I might have taken in this direction, some might have got tilted, and of course definitely there is a shift here, so I need to compensate if there is any tilt there, and then I need to place them, move them such that they are both like a continuous version. There the common region is matching nicely between the two. Okay, I think you have now enough?
Sir, I have one doubt.
Yes, please.
Uh, that panorama, the image stitching, what every time we take it as a horizontal,
Hmm.
the overlap is between along the x-axis.
Hmm.
If it is overlap is along y-axis, means it is like a vertical panorama, is still will
No,
be
no, no.
same or
It's nothing to do about vertical panorama or horizontal panorama. Maybe I would not use the word panorama because how it is used and whether it is technically correct or not, I am not very sure. So let me use just image stitching the word here. So I have one image like this. You could even in fact have y. Just in that case, all I need to do is I should also take care into the translation happening in y-axis. So when I am saying image stitching, this word is generic enough. Hopefully that panoramic view also should be generic enough to involve that. But to simplify things, in your camera he would be showing two horizontal lines telling you that look, you are diverging from or making a move in the y-axis, so you better keep that, make sure you move it properly, otherwise your bottom part, because when the moment you are capturing here, the information here is missing, so there is no way you could you smoothly make an interpolation there unless you are taking only the common region. Okay, that's why they would put an constraint on moving it only in this direction, not make any move in the y direction. But when we are discussing about it mathematically as a computer vision person, so there is no restriction on whether it has to be in horizontally or vertically. All that we impose here is that the translation in y-axis and translation in x-axis also you need to take into account while you are computing the transform. Given this, assume that here also one more thing we are assuming, are taken for granted rather than saying assuming, is that you already know correspondences of which key points are which is the key point here that corresponds to a given key point here. Okay, otherwise this would be again at least 2 3 classes it will take. But it is we could simply assume here, consider here, that you have a very efficient descriptor. You take a, let's say, the Euclidean distance between these two vectors of descriptors of 1 cross 128 vectors you had got from SIFT, and assuming that if that which is having a minimum distance, okay, or maximum difference, sum of square differences between the vectors is already telling you that these are the matching key points. Okay, otherwise that would be again 3 more classes it could take. So this technique is good enough for us. Okay, later, unless if you are going to work on finding out, then you could dwell more detail later individually. But for the sake of other important topics that we want to look into, this is what you could take for granted. Okay, you are given the corresponding points. Now you want to transform one image into the other image that it is look alike of the other image in terms of its size, shape, orientation, and everything. Okay, so this correspondence is also, hope that is clear before we move on and figure out how to find out these transforms given two images and the key points that are matching in those two images. That's the problem that we are posing here. uh, let's say now he's calling it yeah, is xi here. Whenever he's writing it in bold, it means a vector there. You have set of points I varying from, let's say, 1 to n. You are given n key points here in the same order. They are matching here. You have here also this I1 to n, and x1 and x1 prime are the corresponding points that you know. So suppose if it is xi here, the matching point here is also, if it is xi prime here, xi is matching with xi prime. So are you getting that these are the two key points which are same? Okay, but because of the viewpoint, scale, zoom in, zoom out, rotation, you got a, the indexes would have changed. So let's say if you consider here as x and y, that index has changed compared to that, and here if you are taking the x and y. Now the job here, to put it mathematically, is to find out the parameters p and a transformation function f, that if you give it the x values, that means the values here, then applying this transformation on it, would give you the points, set of points x dash. So our goal now is to find out, okay, the best estimate of these parameters, such that when you apply it, whatever points you are getting are very close, okay, ideally the same as what you have here in x dash. That's how you could pose the problem here. Again, we restrict ourselves here to 2D. Later extension to higher dimensions is straightforward in most of the cases, that you could see depending on if you need to further work on it. But for now, we assume just 2D transformations. Assume that there is an image something like this, just to give you some feel of what these transforms would look like. Translation is pretty simple, okay, just the indexes would be like shifted in both x and y. Rotation, assume that again this rotation could be with respect to different points, but in our study here we assume that the rotation is with respect to the origin. Then the third one you could see here is, this is just to give a feel of how the images look like for different transforms. Then that's aspect ratio change, okay, that's something would look like that. Affine, okay, in addition to the scaling effect, it could have a sharing also, sharing. Those who have done some basic mechanical engineering course like engineering mechanics and all should be knowing the sharing to apply on the surfaces which are a tangential force. Okay, you take a something, an object, and you apply a force, one in this direction, okay, and another in the opposite direction. So the kind of deformation you get can be represented by a transform which is affine. Something looks like this. Perspective, with 3D object from a different viewpoint and all these things, you would get something. We would come back to it after some classes again. Cylindrical, now this you could think of some camera which is there, cylindrically shaped one is there, on which you are capturing his image. Okay, this you might have seen in some places where the object gets into this particular shape, different from the original. These are some kind of transformations that you could think of. Suppose in the first image I have an object like this, okay, my x and y are like this, and in the second image this had turned out to be in this manner. Okay, this is what had happened when I moved from the first image to the second image. So the question is now, let me call the second image values as, sorry, x dash, and first image values of indices there as y dash there. So what would be, how can I represent x dash in terms of x here? Okay, so and y dash in terms of x and y here.
For
Yeah,
some alpha times x and beta times y.
that's all very good. Beta times y. Okay, now I want to go one more step forward and deal with everything as vectors. Okay, the reasons and the conveniences and comforts that you get because of using the vector representation would become clear to you in due course of time. But for now, you take it for granted that you have to represent them in like vector and matrix notations. So let me, in that case, x dash comma y dash equal to some matrix here into xy. So this is giving me the transformation that I need to apply in order to get the new coordinates. So what is that matrix M now here that I need here?
Alpha 0, 0
Alpha
beta.
0, 0 beta.
That's all, right? This is all you need to do for scaling. And if your algorithm, all you need to find out is you use some metrics and find out alpha beta. And after that, on this image, given image, you apply this, multiply it with this matrix equivalent to applying this transformation, and you would get the second image. Okay, clear? Then next question is shear. So you could see here when you are applying shear, the shape is probably clear to you. Equation maybe are not everybody might be very comfortable with this. So let me write something here. So it would be something like this: y dash equal to y plus ax. You notice here earlier some you have an object like this. So when you are doing it in this manner, the x based on the location of y, it's the slope it is linearly varies with respect to y, okay, depending on whether it is positive, negative, and so on and so forth. So this is how you could represent a shear. Okay, x dash equal to x plus ay, that x location would be moving accordingly. It could have been moved opposite. So in this case, for example, a is negative for what you see there, and similarly y dash equal to y plus ax. So now you tell me x dash y dash equal to some matrix here multiplied with x comma y,
1A.
right? Okay, let me use different scales here. Okay, let me call this as b here. Yeah, now you tell me.
B1.
That's all. This would give you sharing. You simply find out a and b, two parameters to be computed. It's enough. You take 2 points and do that, right? So that's sharing, or in fact, one set of points are good enough there, not 2 points. It's a set of 1 point has 2 indices. We'll come back to that. Don't worry. I don't want to make it complicated at this point. So 1A and B1. Okay. This is sharing. Next question is, I rotated a point with respect to the origin. So original point is like this. Okay. Now I rotated this point with respect to this origin. So assume that the whole object is rotated, but I'm showing you here one point here. So now how is x dash? So this is theta here. Okay. Then the new one is x dash. Okay. Again, that is x dash y dash. If I'm writing it in terms of scalars, again, I have a matrix here and x comma y. What is this one now? If I give you this theta, you all know rotation of coordinate axis, you have been doing it so that you could use it, and just you rotate it in the opposite direction in theta. That's one way you could do it. And for that, I'm sure most of you remember the this formula also: x dash equal to x cos theta minus y sin theta, y dash equal to x sin theta plus y cos theta. So here it is equivalent to rotating your coordinate axis in yeah, there you are, your point is moving in that direction, so you just need to figure out its equivalent to, I think, anti-clockwise itself. That you could figure out. That's one way. Okay, that by that I think you could all relate that with these equations that you have seen earlier. Another way that this guy has solved is also nice. What it is done is, for example, if this is r, if you consider you are rotating it here, then still this value is still r here, correct? And assume this is given as theta already. Assume that this is equal to phi. Okay, now this is your x dash and this is your x, okay, bar vector. Okay, now I could write it as, for example, now if you write it as, let me write it as without the vector notation. This is x dash y dash x comma y, right? Now you tell me in terms of r, theta, and phi, what is the value of x dash here? X dash equal to, sorry, x dash, yeah, not without this vector, simple x dash, this value. What is this value? X dash equal to, come on,
R cos theta plus phi.
r cos of theta plus phi, right? Y dash equal to r sine
R sine of
theta plus phi. What about x now? X equal to
x cos of phi.
r cos phi, right? This is r. Y equal to r sine phi. This is good enough for you to express x dash y dash in terms of the other. So you just expand this: r cos theta cos phi minus sin theta sin phi. This is r sin theta cos phi plus cos theta sin phi. And then you, for example, here you want x dash y dash in terms of x and y, and you need to simply get rid of this phi. That's all. So if you look at here, For example, after r cos phi is equal to x, okay, that's coming as x. Here r sin phi you get, that's equivalent to r sin phi is y, so you simply take y here. Similarly, y dash, when you are expanding this sin theta cos phi cos theta sin phi, r sin phi, okay, that's why we have seen it, okay. So that then this is y cos theta, okay, this would come here. And similarly, r cos phi sin theta is equal to x sin theta. That's all. You get these values. Okay. Now, can you now tell me the matrix representation for it? X dash, y dash equal to matrix of x comma y. What is the first row now?
Cos theta minus sin theta and sin theta cos theta.
That's all. Minus sin theta, cos theta. That's all. So with this transformation, you are able to represent that. That's all that has been done here. Okay, so far whatever transforms we have considered are pretty well behaved and pretty sincere, falling into the groove nicely, where x dash y dash it's equivalent to get, in order to get it from xy, all you need to do is simply multiply that with a matrix, okay, and that matrix has p parameters, for example, which you have seen there, and you just need to find out this matrix M, which would tell you what are these parameters. These two are related here. So this is again some more extensions and which you could figure out that they are correct just by observing them. Scaling, you have seen it already, this you have worked out. So you just see here, in order to see, just multiply it with xy here, you keep here x dash y dash here, that will tell you that matrix. So x dash equal to sx times x, so sx xy, you have these values in case of a scaling. Okay, now suppose you want to flip an image around y axis, then what would happen? Y value would remain same, right? But x value should become minus x, is it not? So from that, won't we you able to see here, for example, if I have xy here, x dash y dash on the other side, x dash equal, this is giving me x dash y dash. You could see here x dash equal to minus x and y dash is same as y. Okay, similarly, I can ask you n number of things. How about flipping around the x axis? Then what would happen? If you are flipping around the x axis, what would be the matrix then? What is the
1
matrix?
0 0 minus 1.
That's all, right? So then what I would get, if I multiply it with xy, then x dash equal to x, y dash equal to minus y. You could write in that manner. Okay. Now, similarly, rotation you have worked out. Flipping across the horizon, so that means both x and y, both flips are there. Okay, so that's a combination of these two will be there, which would give you diagonal elements with minus. Shear, you worked it out already. Identity, that means x dash y dash equal to xy I should get, so obviously a unit matrix here. Okay, now tell me the matrix M when I am making a 2D translation. By that, what I mean is, let's say my x dash equal to x plus tx, translation of t subscript x I am applying in the x direction, y dash equal to y plus ty. I'm translating the object by a constant ty. And of course, now my parameters are tx and ty, which again we want to put into a very generic mold of M that we have discussed so far. So now tell me, what is that? X dash y dash equal to something into xy. So what is this now? I'll give you, so one simple way to write it down is x dash y dash equal to xy. If you look at multiplications are, for that is with 1 here. So I could check here 1 1, and then here there is no term of y here while computing x dash, so this can be 0. Here there is no term of x here, so the x coefficient is 0 there. Then after that, what I could do here is I could separately have one more term here, which is equal into plus what can I have here? First tell me the size of it. What is the size of this matrix?
2 cross 1.
2 cross 1. Now you tell me the first element. First element here.
Tx, sir.
Right. Tx, Ty. Is that fine now, representation?
Sir, but this TXTY can be added like a third row in the first matrix.
Yes, that's what I want you to do that. Okay. Now what I would want you to do is I want everything in one matrix. Okay. I don't want to keep track of so many matrices here. So that's what I leave you with. How can you don't now restrict the relaxation given to you is you no more need to restrict to a 2 by 2 matrix. I give you the freedom to expand further there. Okay. And then have a still I couldn't have a matrix here m. It is up to you to figure out the size, but at the end of the day I should get x dash bar equal to some matrix into x bar. Okay, this is what I want. So think about it, and we will continue our discussion on this further on how this matrix M would be. Okay, this is very useful, and the impacts of what we are doing, the reasons for doing it in that way will become more and more clear to you as we move on. And even more so once we come to perspective projection, the interpretations for it also, you will get it in a very nice way. Okay, but anyway, till then you don't have to wait. You would be keep understanding some, getting some intuition about why this kind of representation is convenient. Okay, I'll stop here. Do you have, so this is what I leave you with. You work it out by tomorrow. Okay, then we will continue from here in tomorrow's class.